Look closely at the Thar Desert sand to find microscopic marine shells. This arid expanse is the physical archive of an ancient, evaporated ocean. Today, this northwestern desert region dominates the geography of Rajasthan. It covers roughly 209,000 square kilometers, accounting for 61.11% of the state's entire landmass. Following recent administrative restructuring, this vast expanse now encompasses 19 districts, defining the physical and economic reality for nearly 40% of the state's population. The desert is contained by two rigid boundaries. To the west lies the Radcliffe Line, forming the international border with Pakistan. To the east, the Aravalli mountain range acts as a towering natural watershed. Because it sits squarely in the rain shadow of the Aravallis, the southwest monsoon winds are blocked. The region is starved of moisture, receiving a meager 20 to 50 centimeters of rainfall annually. The proof of its oceanic past lies in its chemistry. This infographic illustrates the rudiments of the Tethys Sea. Beneath the sand, salt rocks push salinity to the surface via capillary action, creating inland salt lakes and leaving marine fossils in Jaisalmer. What we see today is a desiccated basin, a prehistoric marine ecosystem that retreated due to tectonic uplift, leaving behind a landscape governed entirely by the harsh physics of drought. Climatologists divide this desert using a strict mathematical line, the 25-centimeter isohyet. This rainfall contour separates the true arid Great Desert in the west from the semi-arid steppe to the east. Within that western arid zone, 58.5% of the land surface is consumed by active, migrating sand dunes, driven by constant wind erosion and deposition. Yet right in the middle of this sandy expanse exists a structural anomaly, the dune-free tract. Covering parts of Faloti and Pokhran, this is a hamada, a stony, barren plateau, completely devoid of sand dunes. Jaisalmer sits directly on top of this stable anomaly. Its famous fort is anchored into exposed sedimentary sandstone dating back to the Jurassic period. The Thar is highly variable. It is a patchwork of shifting aeolian dunes and ancient exposed bedrock, requiring entirely different strategies for human survival. Where the sand is thickest, wind shapes the terrain into specific aerodynamic structures. The most aggressive of these is the Barchan, a crescent-shaped dune that forms in areas with high wind velocity and zero vegetation. This technical diagram details the Barchan's anatomy. Wind strikes the gentle windward slope, pushing sand forward to form crescent arms pointing downwind. Between these arms lies a depression. Wind friction carves out a trough called a thali, acting as a catchment for rare rainwater. Lacking a stabilizing root system, Barchans are highly mobile. They physically migrate across the landscape, burying roads and settlements, acting as primary agents of desertification. This geographic migration is most intense between March and July, particularly in districts like Churu and Jaisalmer. The Barchan operates as the mechanical engine of the desert's expansion. Driven by velocity and unrestrained by flora, it is a continuous force of geographic consumption. This diagram shows transverse dunes. These ridges build up at an exact 90-degree right angle to a prevailing wind that blows consistently from a single direction over long periods. Found heavily in the semi-arid northern and eastern districts like Bikaner and Hanumangarh, these transverse ridges remain relatively stable compared to the shifting Barchans. By contrast, longitudinal dunes, sometimes called linear or scythe dunes, form parallel to the wind, stretching out in long vertical lines across the western and southern reaches of the desert. Geomorphologists explain these parallel lines using the bimodal wind theory. When the wind shifts seasonally between two distinct, narrow angles, the converging airflows pull the sand into tight, straight ridges, rather than pushing it into waves. Because their geometry is dictated entirely by aerodynamics, the dunes of the Thar function as a massive geological compass, recording exact historical wind patterns across the subcontinent. Spread across virtually every desert district are parabolic dunes. From the air, they resemble massive hairpins curving across the landscape. This diagram illustrates their unique formation process, known as deflation. Wind scours sand from the center of a plain, but native vegetation grips the outer edges, anchoring the arms in place while the center bows outward. While parabolic dunes require vegetation, star dunes require chaos. They develop where wind patterns are highly irregular. Returning to the chart, multiple conflicting wind vectors converge, pushing sand into a central peak with arms radiating outward, common near Mohangar. A barchan indicates an active, destructive wind, but the stabilized arms of a parabolic dune prove that, historically, this region had enough moisture to support the vegetation necessary to lock the sand in place. Deep beneath this arid surface is a geological contradiction. This infographic maps the Lathi Series, a 60-kilometer-long subterranean belt of sweet water trapped in ancient rock between Pokhran and Mohangar. This aquifer is the desert's most vital lifeline. At its heart is the Chandon tube well, famously dubbed the Pitcher of the Thar, which taps directly into this massive buried reservoir. The presence of that deep water points to a radically different climate. Here, in the Akal Wood Fossil Park, exposed Mesozoic rock from the Jurassic period provides the physical evidence. 180 million years ago, this precise location was a dense, humid tropical forest. Over millennia, massive gymnosperm trees were buried under sediment. Through a process called permineralization, silica-rich groundwater seeped into the wood, replacing the organic cellular structure with solid stone, perfectly preserving 13-meter-long logs. The modern Thar Desert survives by drawing on the ancient capital of its past. Its cities and agriculture rely on the deep aquifers and stable bedrock laid down when the region was still a tropical jungle. To survive here requires strict resource management. This chart details the region's indigenous hydrological engineering, showcasing structures like the Kadin for farming and the covered tanka for capturing rare rainwater. The most architecturally sophisticated of all these are the bari, or stepwells. Deep, multi-leveled stone structures designed specifically to access fluctuating groundwater while shielding the surface area from intense evaporation. Today, modern science supplements these traditional methods. Institutions combat desertification using the checkerboard method, planting grids of 7 grass and acacia trees to physically lock migrating barchan dunes in place. The ultimate defense is macroengineering. The Aravalli Green Wall project aims to cultivate a 5-kilometer-wide ecological barrier of native vegetation along the mountain range to permanently halt the eastward march of the sand. The Northwestern Desert is a landscape defined by extremes. Thriving here means understanding the deep geology of the rock, the aerodynamic physics of the sand, and the precise engineering required to master every drop of water.